All right, guys, we are going to continue working on Chapter 6, which is all about confidence intervals. In 6.1, we discussed a few different things. We defined a confidence interval. We talked about finding the z-scores, which relate to different confidence intervals, which are also called the critical values. We discussed how to find the margin of error. We were given a formula. We were given a formula to determine the minimum sample size. So we're going to continue with 6.2 today. But before we get started on that, which is confidence intervals for the mean with sigma unknown, meaning we do not know the population standard deviation, I want you guys to pause, work on this warm-up from 6.1. It's all about determining the minimum sample size, so you'll need to go back and look at that formula. All right, so let's get started here. So we've got this soccer ball manufacturer. They want us to estimate the mean circumference of soccer balls within 0.1 inches. So this little value here that we're going to need is actually going to be our margin of error. So 1 second here. It's going to be our margin of error. And our margin of error, E. So I'm just going to write down, oh, I don't want it in that color. Let's get some black here. So we have E is equal to 0.1 inches. Okay, E equals 0.1, because we will need this in our formula for sample size. So now it asks us to determine the minimum sample size. Determine the minimum sample size required to construct a 99% confidence interval for the population mean. Assume the population standard deviation is 0.25 inches. All right, so the great thing about this is we have a formula for it, okay? And the formula that we're going to use, let me just write this down here, all right, is N equals Z sub C times sigma divided by E, and then we're going to square the whole thing. So we've already got a lot of this information here, and I kind of tried to go through and highlight all of it. We don't have Z sub C. We don't have our z-score for our critical value. Our critical confidence interval is 99%. So you could just use your chart. You could use the calculator if you didn't remember what it was, but we have a chart for commonly used confidence values, and 99 is one of them. And so we could just reference that chart, and our critical value here would be 2.575. Okay, so we just go ahead and we sub all these numbers in. We have 2.575 times our standard deviation, which is 0.25, all divided by 0.1, and then we're going to square the entire thing. We get about 44.4, but remember, you are not allowed to have a portion of a soccer ball, so in this case, we always round up and we get 45 soccer balls. Okay, so the minimum value we would need in order to construct a 99% confidence interval for that mean would be 45 soccer balls. Okay, so part B is going to ask us to do the same thing, but instead of using a population standard deviation of 0.25, we're using a population standard deviation of 0.3. So we have N equals, we're using the same critical value, times 0.3 divided by 0.1, and then we're going to square the whole thing. We end up getting about 59.7, which we are clearly going to round up to 60 soccer balls. Okay, let me just move this up a little bit. All right, so now it's asking us which standard deviation requires a larger sample size. And clearly the standard deviation in part B requires a larger sample size. So we're just going to go ahead and say that, oops, let me get my pen here. Larger standard deviations require a larger sample size because the data is more spread out. All right, so let's continue on with kind of our objectives for 6.2. So we are going to introduce something called the t-distribution, and we're going to use a t-distribution table. And with that t-distribution table, we are going to construct and interpret more confidence intervals for a population when the sample standard deviation is not known, okay? So we do not know the sample standard deviation. So that would be sample standard deviation. All right. Okay. All right, so let's get started on our t-distribution, some of the different properties of a t-distribution. So here are properties of a t-distribution. So first of all, our population standard deviation is not known. Population standard deviation is not known. Okay. Next, our sample size is less than 30. Our random variable x is approximately normally distributed. So this one's a little bit different because in 6.1 we didn't necessarily have a normal distribution, but our random variable x is approximately normally distributed. And last but not least, our critical values are denoted by T sub C. Okay, so in 6.1 we were using Z sub C. Now we're going to be using T sub C. All right, so properties of the t-distribution. Okay, properties of the t-distribution. The mean, the median, and the mode of the t-distribution are all equal to 0. The t-distribution is bell-shaped and symmetric without the mean, so we're looking at that normal curve here. The total area under the curve is 1, or 100%, which is typical. The tails in the t-distribution are thicker than those in the normal distribution, so I'll show you guys that when we get down there. But the tails are thicker. The standard deviation of the t-distribution varies with the sample size, but it's greater than 1, so our standard deviation is always going to be bigger than 1. The t-distribution is a family of curves, each determined by a parameter called the degrees of freedom. Okay, so this is important here. We're talking about a new little vocab word. So the degrees of freedom are the number of free choices left after a sample statistic, and this should say in here x, sorry, I'm still not very good at using this stylus, x bar is calculated. Okay. When you use a t-distribution to estimate the population mean, the degrees of freedom are equal to 1 less than the sample size. So let's zoom in here. So the degrees of freedom are equal to 1 less than the sample size. So df equals n minus 1. And then finally, as the degrees of freedom increase, the t-distribution approaches the normal distribution. After 30 degrees of freedom, the t-distribution is very close to the normal, standard normal. So as you see here, we have a family of curves. I know it's a little bit hard to see. I think it printed out hopefully a little bit better on your notes. But we have thicker tails. So this is what I was talking about before when I said the tails were going to be thicker. So the tails here for this one are pretty significantly high above that t-axis, and that's when our degrees of freedom are 2. So then our next one, we have degrees of freedom are 5. That would be here. And then we have that standard normal curve is going to be this blue one, and you can see that the tails get thinner and thinner. Okay, so the higher the degree of freedom, the closer it is to approaching a standard normal. So therefore, the tails get a little bit thinner. All right, so finding a critical value for a 95% confidence interval when the sample size is 15. So if you look at the PowerPoint notes, you'll be able to see on the PowerPoint notes that there is a little snippet of a chart, and we need to use that chart in order to calculate our critical value T sub C. It's very much like everything we've been doing. You either need to use a chart, you could use technology, but we're for now going to be using the chart, and I'll post that on Google Classroom so you have access to it. So find the critical value T sub C for a 95% confidence when the sample size is 15. So on the left side of the chart, we have DF, which is degrees of freedom, and then the top has level of confidence interval. So we need to calculate our degrees of freedom first, and remember, degrees of freedom is equal to n minus 1, our sample size is 15, so our degrees of freedom would be 14. So we would go over to the left side, go down to 14 because that's the degrees of freedom, and then it's a 95% confidence interval, or a 95% level of confidence. So we go over to the top of 0.95, and we get our T sub C, our critical value is 2.145. Okay? All right, so confidence intervals and T distributions. We've got some more things that we have to write down here. All right, so here's how we construct a confidence interval using a T distribution. First, you need to verify that sigma is not known. Just erase this. I don't know why that won't erase. All right. So we have sigma is not known. Sample must be random. So sample is indeed random. And the population is normally distributed. Okay. Next, we identify the sample stats. We're going to have our n value, our x bar, and our s value, which is going to be the sample standard deviation. Next, we have to identify our degrees of freedom, our confidence level, and our critical values. Next, we find E, for which we have this formula. It's going to be our critical value times our S value, which is our sample standard deviation, all over the square root of our sample size. Next, we construct our confidence interval, which is X bar, the mean, minus our margin of error. And then we have X bar plus our margin of error. And then finally, we're going to interpret this whole thing. Okay, so let's take a look at an example here. I'm going to do this one example, and then I will assign you guys some homework problems. Okay, so constructing a confidence interval. You randomly select 16 coffee shops, so I'm going to highlight all of our pertinent information here. 16 coffee shops, and measure the temperature of the coffee sold at each. The sample mean temperature is 162. Sample standard deviation is 10. Find the 95% confidence interval for the mean temperature, and we are good to go. Okay, so let's write down kind of all our little information here, that all the variables that we have. So we have, I don't want that color. Let's try this again. Okay, we have X bar, the mean, is equal to 162 degrees. We have What else do we have? We have our sample size, n, is 16. Our sample standard deviation is 10. And our confidence level is 0.095. So now we have to identify the degrees of freedom. So the degrees of freedom is going to be 16 minus 1, which is 15. We use our table to find our critical value. So we would go over to degrees of freedom of 15 and a confidence level of 0.95. We our margin of error, which is 2.131 times 10 divided by root 16, which is about 5.3. And then we have, we do our confidence intervals here, x bar minus e and x bar plus e. We end up getting that our mean is somewhere between 156.7 and 167.3. So then when we interpret this, we say with 95% confidence, you can say that the population mean of the temperature of coffee sold is between 156.7 and 167.3 degrees Fahrenheit. And this right here would be our answer. Okay, but then when you write it out, you would have to actually write out the interpretation like I had just said. All right, so what you guys are going to do out of this packet, you are going to do, let's see, the car problem, and the following two problems are going to be homework. So this problem here is going to be homework. That's homework number 1. And then if you look at the back of your notes, numbers 17, and then we'll say, and numbers 17 and 18 are also going to be homework. Okay, so complete all those. And then you can check your answers on Google Classroom. If you have any questions, please post them here. And then whatever does not get answered by your classmates, I will absolutely be able to answer. All right, guys, good luck with your first assignment. Let me know if you have any questions. And if not, I will chat with you again tomorrow. Have a good night.